Zašto nisam učio ne gramatiku ovdje? Još ti jesam to učio. Super, super.
And yes, what I would like to speak today is about the gravity theory on non-commutative space. And this work originates from collaboration with the Munich group. And what I will say today will be soon published. So, thanks to Banja, I can skip motivations because there is a lot of overlapping. Let me just say that for me the most convincing argument is a very crude and base argument. General relativity plus quantum mechanics give a quantum gravity, whatever it is, but general relativity is geometry. The observables are space-time properties. Quantum gravity is not commutative observable, and if I put commutative observables where the observables are space-time properties as well, I should get some kind of commutative geometry. So that's why I'm interested in formulating a gravity theory of a non-commutative space-time. The approach I will follow in studying this theory can be described, generically said, as a non-commutative diffeomorphism approach. What I mean by these three words? Well, I consider a space with a given non-commutative structure, and the idea is to consider, so this non-commutative structure in general is not compatible with the general arbitrary diffeomorphisms. So either I reduce the number of diffeomorphisms that are compatible with the structure, like I have, let's do the symplectical limit. I have a symplectic structure, I can just go to the Hamiltonian vector fields, or I can deform the algebra of diffeomorphism in order to have a symmetry that is as big as the initial, as the commutative one. And this is the philosophy that we are considering. And in order to, and this philosophy is very close to what, in the case of the finite dimensional algebra instead of the infinite dimensional algebra of the diffeomorphism. This philosophy is quantum philosophy. And well, also, for example, recently has been applied to the theta constant Minkowski space and the form of the Lorentz group that has is as rich as the form Poincare group that is as rich as the initial commutative Poincare group, this called the theta Poincare group that has been started by Stumpf and the rest, and charge on the equation. So let me also add that this approach is different from what we have heard earlier by Maya and by John Magor, because, for example, I will never at this initial stage speak about killing vectors, and so for me, non-commutativity and curvature of space-time are two aspects that that are not reciprocally constrained. So in the end, what I want to do is to write down some Einstein equation in a non-commutative space and see how the curvature, which are solutions of this Einstein's equation in this non-commutative background. So in order to proceed, well, I have to construct a non-commutative differential calculus. I have to speak first of all about non-commutative differential geometry. So let me briefly recall the usual case. The usual case, I start with the manifold, and I go I consider together with it the space of vector fields. Dual to them is the space of vector one forms. I consider exponential calculus, but I can do more. I can do more geometry, introduce connections, and therefore introduce a curvature, a Ricci tensor, and then next step, use the metric aspect of the geometry, Euler-Riemann geometry, and derive the Einstein equation. So what I would like to do is to repeat this sequence of steps in the non-commutative case. And of course, in the non-commutative case, instead of the manifold, I will have to consider the non-commutative algebra A, that is a deformation of the algebra A of the functions on M. Functions on M with the usual pointwise product. Now, this program has been carried out in the theta constant case, and we're presently trying to generalize it to a generic non-commutative product that is obtained from a given Poisson structure via Kontsevich quantization equation, so a star product. In this talk, what I present is a non-commutative manifold that are characterized by a star product that is more general than the theta constant one, but that is not as general as the Kontsevich one. And they are called twist, and I will describe soon what class of star product we consider. It's quite a general class. Let me add that in this context, as I said, non-commutative diffeomorphism plays an important role. So let me just recall that the algebra of vector fields, the algebra is important because this is tells me what infinitesimal coordinate transformations are. Out of this the algebra, I can construct the universal enveloping algebra that I will call the universal enveloping algebra of vector fields. Well, this is just taking a vector field and considering product of vector fields and the modulo of the commutation relation between vector fields. So in general, this will be an element here. And this is a Hopf algebra with a coproduct that on the basic elements of vector field is the usual commutative product. And this Hopf algebra is a mathematical way to say that this structure encodes the group of diffeomorphisms on this manifold. Okay? So the point that I want to make here is that vector fields comes with this group structure, and non-commutative vector field will come with a non-commutative group structure. And the knowledge of the non-commutative group structure will be essential to do the non-commutative geometry I'm describing. Notice though that as algebras, this and this are the same, not as a object. So there is also another bonus in doing, in considering this lower line in the case of twist, is that one is able to keep under control global aspects. So instead of being obliged to work on the ovens of Rn, well, that's still interesting because, of course, gravity. First of all, it's a local theory. I can also describe global aspects of this non-commutative theory. So let's enter a little bit more into the details of this structure. And so let me start saying which kind of non-commutative product I will consider. So star products from twist. And let's start with an example. This is the theta constant case. This is a constant theta, product of two functions h and g. And it's given by this expression. And I recognize that here there is an operator that I wrote as f. And this is actually a twist. So let's think of it mathematically about this object. This object starts with 1 plus 1. 1 tensor 1 plus theta tensor another partial derivative. Then there are 2 thetas, 2 d's, 2 partial derivatives, and so on and so forth. So we see that it's a sum of elements, and each element belongs to this space. Okay? So this is an element in the universal enveloping algebra of vector field tensor with universal enveloping algebra. And it is obviously invertible. Here is the inverse of this element, and it satisfies some other properties that, well, in of algebra language are these. What it's interesting for us is that these two vector fields are commutative. And this is a main property that will ensure all these are. So this is an example of a twist. This is an example of a twist. This is the general property of a twist. It's an element in this algebra that has these three properties. And here I want to give another example. Well, this non-commutative space, Q space, can be obtained via twist.
Sorry.
And the twist is, for example, one twist that implements this non-commutative structure.
Sorry, but this particular twist, this is at all related to the wonder group structure of this algebra?
So this is a good point. If I have a twist, I have a quantum group structure. But there are more quantum group structures that correspond, that gives a given non-commutative space. So quantum groups that are obtained via this twist are of quasi-triangular type. Triangular type.
Oh, look. Is it possibly this Q plane with flat connection without curvature?
Yes, yes.
Oh, this one?
Yes. So, yes, now the time is constrained, so, but for example, one can give, using a twist star product on a sphere, it's quite easy to construct a star product on a sphere from a twist. Okay. So let's go further. What is for me a non-commutative manifold in this context? So it's a commutative manifold M plus this twist F. And why I say that this couple is a non-commutative manifold? Because as soon as I have the twist, I can, on my space of functions in the manifold, I can construct the star product. And the star product is given by this formula. So since we will see frequently this formula, let me spend 2 words on the notation. We have seen that the twist is an element in this algebra times this algebra, is a sum of objects, so I can write it as a generic element belonging here plus another element belonging here, and then there is a sum over this structure. I denoted the inverse of the twist, that is again an element in this algebra, with this notation, an F bar. And here, so I first act with F on H. What does it mean acting with F on H? I recall that the F is a polynomial in vector fields. And so I have to act with the first vector field on a function, with the second vector field on a function, so on and so forth. And then take the usual commutative product. This will give me the non-commutative product. So, at this level, we have taken the manifold, we have added extra structure to twist, and we have seen that we immediately get a non-commutative structure. But I can do more. Given the twist, the twist acts also on vector fields. And so what I want to do is, I want to obtain this this non-commutative structure. So let's see how this is doable. As I said, the point is that F has vector fields, but then I can define a deformed Libra. Again, plugging the elements F on these two arguments. And now this action is again, this is the classical commutator of vector field. Another vector field, and then I take again the commutator. Well, this is a deformed derivative, and the vector space, my vector fields, the space of vector fields, as a vector space, is the same, but now has a new operation, that is this bracket. Now, classically, the commutator of two vector fields is just the Lie derivative of the first and the second. So, defining this new commutator, I've just defined a new Lie derivative. I call it a Stark Lie derivative. And, well, the definition is up here. And this is on vector fields, but first of all I want it to have on functions. And well, I have just to copy this definition again using the twist. This is the expression. So okay, these are now the two arguments. This is the universal enveloping algebra element that acts on vector fields. This is the universal enveloping algebra element that acts on functions. This is again a function. This is again a vector field, and I sum over all outputs. Okay, so given this Stark Lie derivative, I can check which is the Leibniz rule associated with this Stark Lie derivative. And well, using of algebra, structured proof that this is the Leibniz rule. So this is an important result because you see, it's a deformed Leibniz rule. The Lie derivative of the first argument is just on the product is just the Lie derivative on the first argument, and then I have to go through with this vector field through these functions. But now things do not commute anymore, and I get a twist. I get this R matrix object that takes into account this deformation that I'm doing, this non-commutative aspect, where the R matrix is the argument universal R matrix that is given by this expression. At this point, I want to stress that here we are doing a calculus, an infinite, these are, the Lie algebra vector field is infinite dimension. But there is a strong analogy with the Vrnjačka differential calculus, in which case he was working in quantum groups, so he had a finite Lie algebra. But this Leibniz rule has all the formal properties and analogies with the Vrnjačka calculus. He's using a quantum group. I'm using here, we're using here a big quantum group, this of algebra. This is a very big of algebra, it's similar of algebra. So the analogy is this, go to the infinite dimensional fields. It turns out that this Leibniz rule is implemented by a coproduct on this algebra here. So, having defined the Lie derivative in this way, we figure out that this algebra can be given, besides this coproduct, a new coproduct that I call star, that can be extracted from this Leibniz rule. Okay, so at this point we are here. We have done these two steps. But I have to add, so we have defined the Lie derivative, this deformed Lie algebra, and the universal enveloping algebra associated with this deformed Lie algebra. Well, one other important ingredient in constructing such geometry is the fact that the vector fields can be multiplied by functions. This I have not yet said. So I have to tell you how to multiply vector fields with functions. So now I have to speak of the fact that vector fields are a module with respect to my algebra A of functions. And also in the non-commutative case, there will be allowed to be a module actually. A module. And so I have to state you what is the product between a function and a vector field. But again, the structure is the same. I have first to apply the twist to these two arguments, and then you will not. Well, it can be checked that this definition is compatible with all the structures I've already introduced. So, for example, the linearity of the function here. And well, this factor was observed already by Majid at the module levels. Given a module, I have a twist. I can construct functorially all other modules associated to the twisted function. Okay, so now we are here, and at this point, given these two structures, it's possible to forget the upper role and to construct the differential geometry, the non-commutative differential geometry, just starting from this data. On the other hand, in the next transparencies, at some time, you will see some relation between what's going on at the lower level and what's going on at the upper level. It's not that I'm obtaining things from up or down. It's just that it's enlightening at each step to be able to compare the two structures. But the construction, once I have these two first building blocks, one can construct all the geometry, the non-commutative geometry. So, in the remaining minutes, let me give you a sketch of how this is done. And actually, formally, well, many of these formulae you've already seen in the previous talk. So what one has to do, one has to, let's see it here, one has to introduce the space of one-forms. The space of one-forms is just a space of functions or the space of vector fields. So instead of saying that the one-form omega acts on V, I just say that there is a pairing between vector fields and one-forms. And this pairing must be a linear in this sense. But when we define this space of one-forms, then I can, on the space of one-form, introduce a name module structure. And this is the way I can introduce a name module structure. The function times the one-form is a new one-form that is defined by its action on vector fields in this way. It turns out that this space is a bimodule. We can multiply functions also on the right. And the relation between left and right is the usual given by the matrix. Then the exterior differential is formally constructed as in the commutative case. The exterior differential of a function h is the one-form d star of h, such that this one-form acting on any vector field is simply the derivative along this vector field on the initial function. And if I'm able to have a local trivialization of my manifold, so if I have a rectangle or just a coordinate system surrounding an open of my manifold, then I can take vector fields Pi and the dual one-forms on the I, and then the exterior differential is written. It is, can be written in this form. That is, the reminiscent of dH is dxi di. Well, this was done remaining everything that is a lower line, but I can compare this calculus with this calculus. There is a way to compare. Turns out that the differential is the same. And this is actually a nice feature. It's what also Kant advocates. Differential is an object with no indices. It should have an underformed Leibniz field. And that's the case for this differential. One can calculate it. And it's an underformed Leibniz field. So, we can construct a covariant derivative of the connection. And again, here, it turns out that it's convenient to use a more abstract geometric notion of connection. So the connection is an object from the space of vector fields in the space, is a map from the space of vector fields in the space of one forms times vector fields. And the fundamental property of the connection is that this map on a function times a vector has to have this Leibniz. Then the connection along a vector field can be calculated via this formula, where this is the paying equal between vector field and one form. So this is a vector field. This element belongs here, and I'm paying this vector field to this one form. But again, here we have the property that if I want to compare the upper row with the lower row, well, then the connection also is a completely geometric object, it's the classical. This is not a problem. Actually, this can be seen as a nice feature. It's not a problem because out of this connection I can define curvature and torsion, and these are not the classical ones. So I will do something different. And again, here I have the definition of, so let's go for a definition of torsion. But you are surprised that this is the definition of the torsion tensor in the classical case if there's no R. But here, every time I'm inverting two vector fields, I have to keep track that there is a non-trivial permutation that is given by this. So this is an interesting ansatz for the definition of torsion, and similarly, this is a natural ansatz for the definition of curvature. And then I check that these are good to define objects. That is, these are tensors.
Hello? When you take the action of the H on the, yeah, can you put it on the other side of the pattern?
Yes. So, sure. R or T. So if I put the action here, if I put H here, this H can go here. And so if I put the H here, it can go here, and it gets a twist by an R. It gets an R factor. So you see, in this context, my objects never commute. They always are commute. So I don't have these commutativity constraints between functions and one forms. They simply are commute.
Are you consistently working with regular
I'm consistently working in a symmetric mode because R is real.
And you can show that R is real. So, I mean,
Yes. I don't have time to enter the real structure, but the real structure can be introduced. Yes.
As they define using a flip, you have a flip there, which is called, well, you don't call it a flip, but a twist. The real structure is defined using the twist.
So, if I want the real structure, it's an extra condition. I have to require that the twist be compatible with the real structure. And this is boils down to a property of the twist F, that the DAG, this conjugation of S, must be the antipode times the antipode times F. That's a property. That's an extra condition on the twist if I want the real structure. But there are plenty of examples where this is case. Okay, so this is actually a good tensor, and here I've written down it really as a tensor. So it's a free form, but since R is there is an antisymmetry property in U and V, the form antisymmetry. It turns out that this tensor lives in this space, and these are. If I want to go to components, well, these are the components, and similarly, one can define the Ricci tensor. Okay, so this was about the non-commutative differential geometry. I've never spoken about the metric, but this is the next step. But by now, I mean, the philosophy is pretty clear. So, what is a metric? Metric is a contravariant to tensor, and in a basis I can write it in this way. Classically it is symmetric. Here we are in this twisted adaptation case, so I ask for an asymmetric property, a star-symmetric property. What does it mean? That if I invert these two objects, I have to twist invert them. I have to invert them with an R matrix. And if I do that, if I flip them with the R, then I have to get back to the original matrix. This is my symmetric property. Of course, I can add metricity and then the non-degenerate aspect of it can be simply stated as that this matrix is a star inverse, and here is the star inverse. One can also prove what in commutative geometry is the fundamental theorem of Riemannian geometry. Given a metric, there is a unique torsion-free connection that is compatible with this. And this works. One can do it using really the commutative argument, where everywhere star products appear. And instead of a symmetrized property, I have to use this asymmetrized. So this also shows that the connections exist, because I have this is a constructive way to obtain a connection depending on the metric. Well, then we are. Well, this is my last transparency. Given a metric. I introduce the inverse metric, so I can also have the two covariant tensor instead of the covariant tensor with this inverse metric. Well, so this is a two covariant tensor. So this is a 2B vector. This is a two contravariant tensor. If I pair them, it's pairing also two vectors two times. And I get the scalar curvature. And with these ingredients, I can write down the Lenson's equations. And now, the formalism is such that care has been taken, that it has been taken care of right action, left action. So it's natural, for example, to write this scalar curvature on the right and not on the left, because of the way the formalism is developed. So you see, this is a non-commutative space, and now I have to figure out the various solutions. So the curvature here is completely, well, the curvature here is what comes out of this equation. Here, of course, this and this tensor are depending on metric and the derivative. Of course, it's interesting then to figure out some solutions of these equations and see which are the deformations of classical vectors and cosmological space-time solutions. Thank you.
Are there any questions?
None.
You have a procedure for deforming a huge solution to the commutative
Einstein equation to come up with a solution to this, or do you expect that in general they won't correspond with itself?
That I don't know. You see, you start from a solution, from a classical equation. That I don't know, because these tensors now are different from the classical. And I don't know whether you can construct a kind of cyber-region map to relate. That I don't know. Yes, that's it.
Other questions? Okay. Before the next announcement, I will give some information. The organizer found some